So good evening all. Welcome to our new session. This weekly we are going to discuss the multiple choice questions from the chapter Relations and Functions. Uh, okay, so we have studied relations and functions in the first year. We know about what is a relation, what is a function, and we were continuing the remaining of uh, the second year, that is relation and function again. And we discussed what is a reflexive relation, right? First of all, we discussed about what is an empty relation, and we know about what is a universal relation. Empty relation is nothing but it is the null set phi, that is a subset of the Cartesian product. If a relation is defined on a set X, and we know the Cartesian product is nothing but X cross X, and we know relation is always a subset of the Cartesian product, right? It is a subset of Cartesian product, and not only that, there is an extra condition, that is the ordered pairs in the relation should have some relation, right? The ordered pair in the relation should they that means those elements should be related in one way or the other. So that is known as a relation, and we know what is a function, right? Function is nothing but it is a specific type of relation in which there is an extra condition. What is that condition? That each element in the first set should have one and only one image in the second set, right? So these are the basic knowledge about relation and function, and we extended those concepts in the second year, and we studied what is an empty relation, what is a universal relation. Universal relation is nothing but the complete Cartesian product, that is X cross X. Now, what do you mean by a reflexive relation? Reflexive relation is nothing but the ordered pairs. We are talking about ordered pairs, and this ordered the all the elements in the set should relate to each other, right? So what do you mean by a reflexive relation? Here you have given the definition. Reflexive relation R in X is a relation with the ordered pair AA belongs to R for all A belongs to X. Suppose if X is equal to set 1, 2, 3. Okay. So if X is equal to set 1, 2, 3, then how will you define a reflexive relation? The reflexive relation should contain the ordered pair 1, 1. Then it should also contain the ordered pair 2, 2. Similarly, it should also contain the ordered pair 3, 3. Like this. This is known as a reflexive relation. And what do you mean by a symmetric relation? The relation R is said to be a symmetric relation if the ordered pair AB belongs to R, then definitely the ordered pair BA should belongs to R. Okay. Now you have studied about transitive relation. What is a transitive relation? A relation is said to be a transitive relation if AB belongs to R and we take another ordered pair, that is BC belongs to R, then definitely AC should belongs to R. So what do you mean by an equivalence relation? A relation becomes an equivalence relation if it is reflexive, symmetric, and transitive. Okay, so these are the topics that we discussed about relation in this chapter. Now we are going to the function. Okay. So what do you mean by a 1-1 function? A function f from x to y, it is known as a 1-1 function, or it is known as an injective function if it satisfies the condition f of x1 is equal to f of x2, then x1 should equal to x2. Okay, that is 1-1 means each element in the first set should have a unique image. It should have a unique image, then such type of functions are known as 1-1 function. So what do you know about an onto function? Onto function is otherwise known as surjective function, right? So what do you mean by a surjective function? In surjective function, we know that if a function is defined from x to y, then all the elements in the y, okay, all the elements in the y should have a pre-image in x. So what do you call this x and y? X is called as the domain of the function and y is called as the range of the function, right? So all the elements in the y, if all the elements in the y contains a pre-image in the x, then we say such functions as onto function or surjective function. Then who is a bijective function? If a function is both 1, 1 and onto, such functions are known as bijective function. Okay, now we are going to discuss some of the problems related to this. Okay, so the first question is, let R be the relation on the set N of the natural numbers, on the set N of natural numbers given by R is equal to the set of all ordered pair AB such that A minus B is greater than 2 and B greater than 3. We have to choose the correct answer. Choose the correct answer. The options are given. First one is 4, 1 belongs to R. Second, 5, 8, ordered pair 5, 8 belongs to R. Then third one is ordered pair 8, 7 belongs to R. Then fourth one, ordered pair 10, 6 belongs to R. Alright, so this is our first question. So they are given a relation. Okay, it is defined on the set N of natural numbers. So what do you mean by natural numbers? Natural numbers is nothing but it starts with 1, right? It starts with 1, 1, 2, 3, etc. It goes up to infinity. So this is the set of natural numbers. So this particular relation is defined on the set N of natural numbers and they are given the condition. Okay, that is they are given the relation in a roster form, right? R is equal to the set of all ordered pairs AB such that A minus B should be greater than 2 and B should be greater than 3. Okay, so we have to choose the correct answer. That is, we have to find the ordered pair that belongs to this particular relation. From the given options, we have to find the ordered pair that belongs to that particular relation. Okay, so how will you do that? In order to satisfy, in order to belong to that relation, that is, the ordered pair should satisfy the condition, right? So we'll check it one by one. So we can start with 4, 1. Okay, we'll start with 4, 1. The ordered pair 4, 4, 1. So what are the conditions that they are given? A minus B should be greater than 2, right? Which means here, instead of A, it is 4 and instead of B, it is 1. So 4 minus 1, that is equal to 3. Is 3 greater than 2? Right. 3 is greater than 2. Okay, so first condition is satisfied. Now we have to check the other condition also. It is said that B should be greater than 3. Here what is B? B is 1. Is 1 greater than 3? No, right. 1 is less than 3. So it is not satisfying the second condition, B greater than 3. Okay, so what can you say that from this? We get that 4, 1. The ordered pair 4, 1 doesn't belongs to that particular relation. Okay, now we are moving on to the second option, that is 5, 8. Can you say 5, 8 belongs to R? We have to check the condition, right? So 5 minus 8, that is equal to minus 3. Minus 3 is not greater than 2, right? Minus 3 is less than 2. The first condition itself is violated. So what can you say? 5, 8 also doesn't belongs to that particular relation. Now check the third ordered pair. It is 8, 7. 8, 7. All right. 8 minus 7. 8 minus 7 is 1. Is 1 greater than 2? No. 1 is lesser than 2. So the first condition itself is not satisfied. So that ordered pair also doesn't belongs to that particular relation. All right. Now, the last one is 10, 6. Ordered pair 10, 6. So what can you say about ordered pair 10, 6? First condition is A minus B should be greater than 2. 10 minus 6 is equal to 4. 4 is greater than 2. So the first condition of the relation is satisfied. Now what is the second condition? The B, that is second element should be greater than 3. B should be greater than 3. Here B is equal to 6. 6 is greater than 3. So from this we got that both of the conditions given in the relation is satisfied by the ordered pair 10, 6. So from this what can you say? 10, 6 ordered pair 10, 6 belongs to that particular relation. Ordered pair 10, 6 belongs to the relation. All right. So this was our first question. Now moving on to the second question. Let R be a relation defined on, let R be a relation defined on A is equal to set 1, 2, 3 by R is equal to set ordered pair 1, 3, then 3, 1, 2, 2. R is, first option is reflexive, second one symmetric, third transitive, and then fourth one is reflexive but not transitive. Reflexive but not transitive. Okay, so they are given a relation, that is the relation is given in the set builder form. It is given as set 1, 3, 3, 1 and 2, 2. It is defined on set A. Okay, set A contains only 3 elements, that is 1, 2, 3, and on this set a relation R is defined and they are given that particular relation. Now what we have to do is that we have to check whether the given relation is reflexive, symmetric or transitive. All right. So how will you check whether the given relation is reflexive, symmetric, and transitive? First, we'll start with reflexive. All right. So we'll start with reflexive. Is that the relation reflexive? So consider the elements in set A. What are they? 1, 2, and 3. 1, 2, and 3 are the elements of set A. If a relation R is defined on this particular set, for that relation to be reflexive, what is the condition? That is, the each elements given in that particular set should relate to one another. Okay, that means if A belongs to this particular set A, then we should get an ordered pair AA. We should get an ordered pair AA belongs to the relation. All right, if an element A belongs to particular set, then the ordered pair A should belongs to R. That is the condition of reflexive relation. So here what we have to do, we have to get the ordered pair 1, 1, 2, 2 and 3, 3 in that particular relation, right? Since 1, 2, 3 are the elements of that particular set. All right, so check whether all those ordered pairs exist in that particular relation that is given. All right, so this contains only 1, 3, 3, 1 and 2, 2. Here you can see that 2, 2 belongs to R, right? Since 2 belongs to A, 2, 2 belongs to R. But what can you say about 1, 1? 1, 1 doesn't belongs to R. 1 belongs to A, but ordered pair 1, 1 doesn't belongs to R. Similarly, 3 belongs to the set A, but ordered pair 3, 3 doesn't belongs to R. So what can you say about the relation R? That relation is not reflexive, right? Here only 2, 2 belongs to R. So we can say that the relation given it is not reflexive. Now what about the symmetric condition? What can you say about the symmetric condition? Is that satisfied? How will you check whether a function of whether a relation is symmetric? That is, if you can able to take an ordered pair AB belongs to R. If you are able to take an ordered pair AB belongs to R, then we should get an ordered pair BA which belongs to R. All right. If you are able to take an ordered pair AB, then you should have an ordered pair BA in R so that the relation will become symmetric, right? So this is a condition. Let's check whether it satisfies all those conditions. So we'll start with 1, 3. So if you take 1, 3, 1, 3, it is an element of R. Now we should find an ordered pair that starts with 3, right? It starts with 3 and it should end with 1, right? So 1, 3 belongs to R. Does 3, 1 belongs to R? Yes, right. 3, 1 also belongs to R. So what can you say? Or if you are able to take, you should check 3, 1 also, right? 3, 1 belongs to R, which implies 1, 3 belongs to R. All right. Now, what can you say about 2, 2? 2, 2 also satisfies the condition of symmetric relation. So, from this, can you say whether this relation is symmetric or not? It is symmetric because every element in the relation satisfies the condition of symmetric relation. So, it is symmetric. Now, we have to check whether it is transitive also. So it doesn't satisfy the property of reflexive relation, but it satisfies the property of symmetric relation. Now we are going to check whether it is transitive or not. So in order to check a relation is transitive, we have to check if we are able to take some AB belongs to R and some BC belongs to R. Okay, if you are able to take ordered pairs AB belongs to R and BC belongs to R, then AC, ordered pair AC belongs to R if it is a transitive relation. Okay, if it is a transitive relation, if you are able to take AB and BC from R, then the ordered pair AC should belongs to that particular relation. All right, so we are going to check whether there is some ordered pair like that, like AB and BC. Okay, so we'll start with 1, 3. 1, 3 belongs to R. So is there any other ordered pair that starts with 3? Yes, there is an ordered pair, right? 3, 3, 1. Okay, it starts with 3. The ordered pair 3, 1 starts with 3, right? So we are able to take two ordered pairs, 1, 3 and 3, 1. Then if it is the transitive relation, it should satisfy the ordered pair 1, 1, right? AC should belongs to R. Here A is 1 and C is also 1. So 1, 1 should belongs to R, right? 1, 1 should belongs to R. But here you can see that is a 1, 1 in that particular relation. No, right? Just 1, 3, 3, 1 and 2, 2. 1, 1 doesn't belongs to R. You are able to take 1, 3 and 3, 1, but 1, 1 doesn't belongs to R, which implies that it is not transitive. It is not transitive. So what can you say from this? The option B is correct. Option B is correct. That is, the relation is only symmetric. All right. So we are moving on to the next question. If R is equal to ordered pair XY such that XY is an element of Z and X minus Y belongs to Z, then the relation R is reflexive but not transitive. B, reflexive but not symmetric. Symmetric but not transitive. An equivalence relation. So R is given as the set of all ordered pair XY such that XY is an element of Z and X minus Y belongs to Z. Then what can you say about the relation R? Okay, so they are given a relation. So we have to check whether it is reflexive, symmetric, transitive, or it is an equivalence relation. All right. So we are starting from reflexive property. That is, if a relation is reflexive, we know that here it is said that the relation is defined on Z. Okay, that is XY belongs to Z is nothing but XY is a member of the set of all integers. Z means it is the set of integers. All right. Z is the set of integers. So X and Y, any element in that particular relation should be an integer. All right. And the second condition is X minus Y should also belongs to Z. All right. The difference of those two ordered pair elements in the ordered pair should be an integer. Okay. So in order to check whether it is reflexive, we know that if X is an element of Z, then if it is reflexive, then XX, the ordered pair XX should belongs to R. Right. Ordered pair XX should belongs to R. So can you say whether the ordered pair XX belongs to R? If XY belongs to R, what is the condition? If XY belongs to R, which implies X minus Y is an integer, right? If ordered pair XY is an element of R, the difference of those two elements in the ordered pair should be an integer, right? X minus Y belongs to Z. So, what can you say about X minus X? What can you say about X minus X? X minus X is equal to 0. Is 0 an integer? Is 0 an integer? 0 is an integer. So 0 belongs to Z, which means the difference of X and X is an integer, which implies from this we can say that ordered pair XX belongs to R. Okay, X minus X is 0. That is an integer, which means it satisfies this particular condition. X minus Y belongs to Z. From this, we get that ordered pair XX belongs to R. Therefore, it is reflexive. All right. So the first condition is satisfied. Now we have to check whether it is symmetric. All right. So for a relation to be symmetric, what is the condition? That is, if XY belongs to R, then YX should belongs to R. Okay. So this is the condition. If it is symmetric, if the given relation is symmetric, then if XY belongs to R, then YX should belongs to R. All right. So I'm taking, let XY belongs to R. Let XY belongs to R. From this, what can you say about X minus Y? From the definition, from the relation, we get that X minus Y belongs to Z. Right. So they are given that if ordered pair XY belongs to R, X minus Y is an integer. So XY belongs to R, then X minus Y belongs to Z. Right. So what can you say about Y minus X? Y minus X also belongs to the set of integers. Right. That is, if I'll give you an example. If 2 belongs to Z, then minus 2 also belongs to Z. Right. If 2 belongs to Z, then minus 2 also belongs to Z. Similarly, here you can see that if X minus Y belongs to Z, then Y minus X also belongs to Z. It is also an integer. So from this you will get the ordered pair YX belongs to R. All right. The ordered pair YX belongs to R. Okay. Now we have to check whether it is transitive. Now it is symmetric. We have got that it is reflexive and symmetric. Now we have to check whether it is transitive or not. All right. So for that, I'm taking PQ. Okay. PQ element of R. It is, you can give any name to the elements in a relation. All right. Here I'm taking PQ because if you take XY, then I should take YZ. The other pair. So it will create a confusion because this is defined in the set of integer sets Z. Right. So I'm taking PQ belongs to R and QR belongs to R. All right. I'm considering two ordered pairs in that particular relation. Since they are the members of the relation, we can say that if PQ belongs to R, if ordered pair PQ belongs to R, from the relation we get that P minus Q belongs to Z. All right. Similarly, if QR belongs to R, then Q minus R belongs to Z. Okay. So we know that addition of two integers is again an integer. All right. That is P minus Q plus Q minus R. We are adding two integers. Adding two integers will result in an integer itself. So P minus Q plus Q minus R also belongs to Z, which implies this Q and minus Q gets cancelled, right? Minus Q plus Q is 0. So P minus R belongs to Z. All right, P minus R belongs to Z. From this, what can you say? PR, ordered pair PR belongs to the relation. P minus R belongs to the set of integers, which means ordered pair PR belongs to R. All right. So from this, you can conclude that it is transitive also. It is transitive also. So the given relation is reflexive, symmetric, and transitive. So we can conclude that it is an equivalence relation. What is it? It is an equivalence relation. All right. So moving on to the next question. Which of the following relations on A equal to set 1, 2, 3. A equal to set 1, 2, 3 is an equivalence relation. Is an equivalence relation. Is an equivalence relation. So the first one is 1, 2, 3. The second option is 1, 1, 2, 2, 3, 3, and 1, 2. Third option is 1, 1, 3, 3, 1, 3, and 3, 1. Fourth option is none of this. Okay, so they are given a set A. A is set 1, 2, 3. So we have to check. They are given a relation A, B, and C. Okay, so we have to check whether the relation A is equivalence or B or C is an equivalence relation. Okay, that is a question. So we'll start with option B. Okay, we'll start with option B. For a relation to be reflexive, it should satisfy a relation to be equivalence, it should satisfy reflexive condition, symmetric condition, as well as the transitive condition, right? So we can check whether the option B is reflexive, symmetric, and transitive, right? So first of all, the condition reflexive. Okay, so these are the elements of the set in A. So in order for a relation to be reflexive, all the ordered pairs should be all the ordered pairs of each element should be there in the relation, right? Which means 1, 1 should belongs to R, 2, 2 should belongs to R, and 3, 3 should also belongs to R, right? So here you can see that 1, 1 belongs to R and 2, 2 also belongs to R. Then you can see that the ordered pair 3, 3 also belongs to R. So the reflexive condition is satisfied by option B. Now what we have to do, we have to check whether it is symmetric. So how will you check whether a relation is symmetric? If you are able to choose AB belongs to R, then BA should belongs to R, right? So I'm taking this 1, 2. All right, I'm taking 1, 2. 1, 2 belongs to R. Okay, so if it satisfies, if that particular relation satisfies the symmetric property, then we know that 2, 1 should belongs to R, right? 2, 1 should belongs to R. But can you say 2, 1 in option B? Ordered pair 2, 1 in option B is, can you spot? No, right? So ordered pair 2, 1 doesn't belongs to R. Ordered pair 2, 1 doesn't belongs to R. Ordered pair 1, 2 belongs to R, but ordered pair 2, 1 doesn't belongs to R. So we can say that it is not symmetric. So the second option doesn't satisfy the property of symmetric relation. So hence we can say that it is not an equivalence relation, right? Now we are moving on to the third option, that is C. That is 1, 1, 3, 3, 1, 3, and 3, 1. First we will check the reflexive property. Okay, so 1, 1 is there. 1 is an element of A. and the ordered pair 1, 1 is there. 2 is an element of A, right? 2 is an element of A, but ordered pair 2, 2 is absent, right? In option C, 2, 2, ordered pair 2, 2 is not there, right? Ordered pair 3 is an element of A and ordered pair 3, 3 belongs to R, but 2, 2 in option C, ordered pair 2, 2 doesn't belongs to R and 2 belongs to A also, right? Even though 2 belongs to the set A, the ordered pair 2, 2 doesn't belongs to that particular relation. So we can say that it doesn't satisfy the property reflexivity. So it is not an equivalence relation, right? Now we are moving on to the first option A. Okay, first option, that is 1, 1, 2, 2 and 3, 3. So clearly it satisfies the reflexive property, right? It satisfies reflexive property, and we can say that it is symmetric as well as transitive. Why we can say that it is symmetric and transitive? We cannot take an ordered pair AB, right? We cannot take an ordered pair AB belongs to R which does not satisfy BA belongs to R, right? Here we are not able to pick such an element. We are not able to pick such an ordered pair like AB belongs to R which doesn't satisfy the property BA belongs to R. So we can say that these type of relations are symmetric as well as transitive. All right, we are not able to take an ordered pair. Okay, then only we can say that it doesn't satisfy the condition, right? So since we are not able to take such an ordered pair, we can say that it is symmetric as well as transitive. So this option satisfies reflexive, symmetric and transitive conditions. So we can say that the first option is an equivalence relation. All right, first is an equivalence relation. Now we are moving on to the next question. That is, let R be a relation. Let R be a relation on a set. Let R be a relation on a set 1, 2, 3 defined by R is equal to ordered pair 1, 1, then ordered pair 2, 2, 3, 3 and 1, 3. Then the ordered pair to be added. Ordered pair to be added to make R a smallest equivalence relation. A smallest equivalence relation. First one is 2, 1. Second one is 3, 1. Then third one is 1, 2. Then fourth one is 1, 3. Let R be a relation on a set A, 1, 2, 3, defined by R is equal to, you are given a relation, then they are asking to find out the ordered pair so that you get a smallest equivalence relation. Like they are already given an R, that is they are given a relation that is defined on set A. Now what we have to do is that we have to find an ordered pair such that it will make a smallest equivalence relation. Okay, such that it will make a smallest equivalence relation. So let's check with 2, 1. All right. Here you can see that it satisfies the reflexive condition, right? 1, 2, 3 are the elements of set A. Here you can see 1, 1, 2, 2 and 3, 3 belongs to R. All right. Now there is an extra element that is 1, 3. All right. There is an extra element 1, 3. Now what we have to check whether to make it symmetric, what we have to do, if 1, 3 belongs to R, then we know that the ordered pair 3, 1 belongs to R, should belongs to R in order to make that relation a symmetric relation, right? So here we are able to take an ordered pair 1, 3. So definitely there should be an ordered pair 3, 1. All right, then it will become symmetric. So if I'm adding option B 3, 1, it will become a symmetric relation, right? Now, what about transitive condition? Transitive condition, if 1, 3 belongs to R and now I am adding the ordered pair 3, 1. 3, 1 is also an element of R. Then we should get 1, 1 belongs to R, right? Then only it will become transitive. Okay, so 1, 1 belongs to R. Whether 1, 1 belongs to R or not, 1, 1 is already an element of R. So if you add the ordered pair 3, 1 to this particular relation, okay, to that particular relation, then that relation will become an equivalence relation because it will satisfy all the three property, that is reflexive, symmetric, as well as transitive. So thus it become an equivalence relation. All right. So what happens if you add 1, 2 to this, 1, 2 to this? Then it will become complicated, right? We have to add the 2, 1 also, right? If you add 1, 2, then you should add 2, 1 also in order to make it symmetric. So it is not a smallest, it will not become the smallest equivalence relation. So they are asking about the smallest equivalence relation. All right. Then 1, 3, option 1, 3 is already an element of R itself. So what is the right answer? Right answer is nothing but B. Okay. Now we are moving on to the 6th question. That is, what is the minimum number of ordered pairs? What is the minimum number of ordered pairs to form a non-zero reflexive relation on a set of n elements? The options are n square, then n minus 1, then n, and then n plus 1. So what is the minimum number of ordered pairs to form a non-zero reflexive relation on a set of n elements? That is, you are given a set and it contains n elements. We have to find out the minimum number of ordered pair in order to form a non-zero reflexive relation. That is, the relation should be a reflexive relation and it should be formed in such a way that we should use the minimum number of ordered pair. Okay, this I'll explain it with an example. All right, consider the set A is equal to 1, 2, 3. Okay, so how many elements are there in the set? It is 3, right? So n of A is equal to 3. The number of elements in the set A is equal to 3. All right, so we have to form a non-zero reflexive relation using minimum number of ordered pairs. We can use only less number of ordered pairs. So how is that possible? In order for this a relation to be reflexive on the particular set A, we know that 1, 1, 2, 2, and 3, 3. Ordered pair 1, 1, 2, 2, and 3, 3 should definitely belongs to that particular relation, right? So R should definitely include the ordered pair 1, 1, 2, 2, and 3, 3. Right. Since 1, 2, and 3 are the elements of the set A, these ordered pairs should definitely be a member of that particular relation. Then only that relation will become reflexive. Right. So, what can you say about the minimum number of ordered pair in order to form a non-zero reflexive relation? It is nothing but 3. Right. If a set contains 3 elements, it should at least contain 3 ordered pair. For that, then only it will become a reflexive relation, right? So if you take set B is equal to 4, 5, 6, 7. So what is the number of elements in set B? That is nothing but 4. So if you are going to define a reflexive relation on B, then it should definitely contain 4, 4, then 5, 5. Similarly, 6, 6 should be there, and also 7, 7. So here, what is n of r? N of r is equal to 4. This relation is reflexive, right? So, and n of r is equal to 4. So what is the connection between the number of elements in a set and the number of elements in a non-zero reflexive relation? It is same, right? So we are asking about minimum number of ordered pair. This become a reflexive relation. So with minimum 3 elements, okay, with minimum 3 ordered pair, we got a reflexive relation on a set of 3 elements. Similarly, we got with minimum 4 ordered pair, we got a reflexive relation on a set of 4 elements. So what can you say about this? The set contains n elements, right? The set contains n elements. So what will be the minimum number of ordered pair for a relation to be reflexive on that particular set? It is nothing but n, right? At least n ordered pair should be there. Then only that relation will be reflexive. Okay, so this is the answer. Okay, n is the answer. N is the minimum number of ordered pair. All right, so we are moving on to the next question. Okay, so now we have completed all the MCQs from the relation section. All right, now we are moving on to the function part. Okay, there are some of the important MCQ from this session also. That is function. The first question is, which of the following which of the following function is which of the following function is 1 1? All right, the options are f from r to r, f of x is equal to x square, and the second option is f from r to r and f of x is equal to mod x. Then third option is f from r to r and f of x is equal to sin x, and the last option is f is defined from r to r and f of x is equal to x cube. All right, so they are asking which function is 1 1. So they are given four options, that is f of x is equal to x square, f of x equal to mod x, f of x is equal to sin x, and f of x equal to x cube. You have to check which of the following function is 1 1. Okay, in such cases, we can either choose our proper rule method, or you can choose the graphical method also. Since this is an MCQ question, you need only mark the right answer, right? You need to write only the option, one of the option. So here you can use either the graphical method or the proper method. All right, so I'll explain both ways. All right, so we know that the function, the graph of the function f of x is equal to x square is nothing but like this, right? F of x is equal to x square. The graph is given here. All right, so in order to check whether a function is 1 1, we have to check if you draw horizontal lines along the graph. All right, if you draw horizontal lines, that is the lines that are parallel to x-axis, if it touches in more than one point, if it touches the graph in more than one point, it is not 1 1. All right, here you can see that. Here you can see that if I draw a line like this, all right, a horizontal line like this, it is touching the graph in this point as well as in this point, right? Okay. In 2 points, they are touching. The horizontal line is touching the graph in 2 points. All right, so we can say that the function is not 1 1. We know that for a function to be 1 1, if more than one element has the same image, right? If more than one element has the same image, then it is not 1 1. It is not. It is a many one function. It will become a many one function. One image, one element should have a unique image, right? So here it is not satisfied. So we can say that it is not 1 1. All right. So this is the one method, or else we know that the definition of 1 1 function, right? If f of x1 is equal to f of x2, then we know that x1 should be equal to x2. Okay, so this is the condition of 1 1 function. F of x1 is equal to f of x2 implies x1 is equal to x2, right? So let's consider f of x is equal to f of x is equal to x is equal to, we'll start with x. We'll take x equal to 2. All right, x equal to 2. So what can you say about f of x? F of x is x square, right? So instead of x, you are putting 2. So 2 square. 2 square is nothing but 4. Now take x1, x2 as minus 2. Another element, x2 as minus 2. So what is f of x2 then? Here f of x1 is 2 square 4. Here f of x2 is nothing but f of minus 2. That is, you have to put minus 2 in place of x. Minus 2 the whole square is equal to 4. Right. So here you have seen that f of x1 is also 4 and f of x2 is also 4. Here you can say f of x1 is equal to f of x2. Both are 4. But what can you say about x1 and x2? Are they same? x1 is not equal to x2, right? x1 and x2 are not same. So what can you conclude from this? It doesn't satisfy the condition of 1, 1 or injective function, right? So it is not 1, 1. It is a many one function. All right. Now we are moving on to the second function. Okay. We are moving on to the second function. That is nothing but modulus function. All right. It is modulus function. So we know the graph of a modulus function just like this. It is defined from R to R. Okay. The function, the graph will be like this, right? So you can check it by our method. That is, if you construct parallel lines to x-axis, horizontal lines to x-axis. Okay, so you can say that these lines touches the graph in more than one point, right? Here you can say that they are intersecting in more than one point. So we can say that it is not 1, 1. So modulus function is not 1, 1. And according to our traditional method, if f of x1 is equal to f of x2, then x1 should equal to x2, right? For that, we'll check with examples. Let x1 be 3. All right. So what is f of x1? F of x1 is nothing but modulus of 3, that is equal to 3. Now let x2 be minus 3. Okay, x2 be minus 3. What is f of x2? F of x2 is nothing but modulus of minus 3, that is also 3. Right. Here you can see that f of x1 and f of x2 are equal. F of x1 is equal to f of x2. F of x1 is equal to f of x2. But can you say that x1 is equal to x2? No. x1 is 3 and x2 is minus 3. Here x1 is not equal to x2. So from this you can say that it is not a 1, 1 function. All right. Now we are checking the third one, that is sin x function. Sin x we definitely know that it is not 1, 1. Why it is not 1, 1? Sin x is a periodic function, right? What do you mean by a periodic function? Periodic function is nothing but a function that repeats in a particular, after particular intervals, right? After particular intervals, the functions gets repeated. Function gets repeated means the values gets repeated. And we know that for a function to be a 1, 1 function, it should have only one image, right? More than two elements should not have an image, right? So we can say that sin x is not 1, 1. And again, with the help of graph, we can say it. That is here, sin 0 is 0, so it starts with 0, and when it reaches pi by 2, it becomes 1, right? It becomes 1. Here it is pi by 2, and when it reaches pi, it becomes 0. All right, so this is the graph of the sin x function. All right. Okay, now if you construct horizontal lines like this, okay, you can see that it is intersecting in many points, right? Here also you can see an intersection, here also, and here also. So there are many points of intersection. So we can say that it is touching in more than one point. So it is not 1, 1. Or else, if x is equal to 0, what can you say about f of x? That is nothing but sin 0, that is equal to 0. And if x is equal to pi, then what can you say about f of x? F of x is equal to nothing but sin pi. Sin pi is also 0. All right. Here you can say that let this be x1 and this be x2. All right. Okay. So we have taken different x1, right? x1 is 0 and x2 is pi, but we got the same f of x1, right? That is here f of x1 equal to f of x2, that is equal to 0. But are x1 and x2 equal? They are different, right? x1 not equal to x2. So what can you say? It is not 1, 1. So sin x is also not 1, 1. Now what can you say about the function f of x is equal to x cube? What can you say? Is that 1, 1 or not? Now only the one option is remaining. So definitely it will be 1, 1, right? So we know that the graph of an x cube function is like this. And if you draw horizontal lines, okay, so I'm drawing many horizontal lines. Is the horizontal line touching the graph in more than one point? No, right? Every line is intersecting the graph in only one point. Each line is intersecting the graph in only one point. So we can say that f of x equal to x cube is a 1 function. And for those who don't know to draw a graph and all, we'll check with the definition. All right. That is, if f of x1 is equal to f of x2. What can you say from this? X1 cube equal to x2 cube. The cube of a numbers, two numbers are equal means definitely that numbers should be equal. Right? Then only the cube will be equal. X1 cube equal to x2 cube means x1 should be equal to x2. From this you get that the function is 1, 1. All right. Now we are moving on to the next question. The function given by f from n to n, f of x is equal to 2x, is, first option is 1, 1 and onto, second one 1, 1 but not onto, third option not 1, 1 and not onto, then the last one onto but not 1, 1. All right. So they have given a function, that is, you have to always be careful about the domain and range of the function. All right. In certain cases, they will be given the function in restricted domain. Okay. In restricted domain, some functions will be 1, 1. All right. So here you have to check the domain, and every time you have to check the domain and range of the function. Here it is given that the function is defined on the set n of natural number. And what do you mean by n? N is nothing but 1, 2, 3. It starts with 1, 2, 1, right? It goes up to infinity. So this is a set of natural numbers. It doesn't have the element 0, right? So on this, you have defined the function f of x is equal to 2x, and they are asking whether this function is 1, 1 or onto. All right. So in this also, you can apply the graphical method also. That is, here you have given f of x equal to 2x, right? F of x is equal to, you are given 2x. So if I give the value for x as 1, 1 belongs to the set of natural numbers. So what is f of x? It is nothing but 2. All right. So if I give 2, it will become 4. All right. So how will be the graph of the function? 0 is not included, and it will be like this. Right. So for 1 it will be 2, and for 2 it will be 4, and similarly the graph goes like this. All right. So if you draw horizontal lines like this, it is touching in 1 point only, right? It is touching the graph in only 1 point. Okay, only 1 point. So we can say that it is 1, 1. All right. But if you draw vertical lines, it is here you can see that these elements, right? It has no image. All right. It has no image. So it is not onto. In according to the definition, we can also prove it. That is, if f of x1 is equal to f of x2. We can prove this way also. Take f of x1 is equal to f of x2. So from this, you can say that 2x1 is equal to 2x2. Right? 2x1 is equal to 2x2. From this, you can get that x1 is equal to x2. Right? x1 is equal to x2. All right. So from this, what can you say? From this, what can you say? It is 1, 1. All right. It is a 1, 1 function. Now, what about onto function? It is 1, 1. What about onto function? Onto function means all the elements in this set should have a pre-image in the first set, right? So if you take x equal to f of x equal to 3, all right? If you take f of x is equal to 3, then what will happen? F of x equal to 3 means here you have given that 2x. F of x is nothing but 2x. 2x equal to 3, which implies x is equal to 3 by 2. 3 by 2 is nothing but 1.5. It is half of 3, right? It is 1.5. Does 1.5 belongs to n? 1.5 doesn't belongs to the set of natural numbers, right? So we can say that it is not onto. If not every element in the natural number have a pre-image. All right. So 1.5 doesn't belongs to n, which implies that it is not onto. All right. X is equal to 1.5. X 1.5 doesn't belongs to n. It doesn't have a pre-image. So it is not, the function is not onto. So it is 1, but it is not onto. Is there any option like that? Yes, B option. All right, the answer is B. It is 1, but it is not onto. Now we are moving on to the next question. That is, which of the following is true about range of onto function? Range of onto function f from x to y. A is equal to range of f is equal to x. Range of f is a subset. Is a subset of x. Then third option is range of f is equal to y. And last option is none of this. All right. So they are asking about the basic property of an onto function. F from x to y, it is a function. It is an onto function. So what can you say about the range of an onto function? If you are properly knowing the definition of an onto function, then it is very easy for you. That is, what do you mean by an onto function? An onto function, and I'm definitely sure that you must know the name of these things, right? A function is defined from a domain to range, and you know that y is the range of the function and x is the domain of the function. So what can you say about the range of an onto function? What do you mean by an onto function? Every element in y should have a pre-image in x. Every element in y should have a pre-image in x. If this is a codomain, this is domain and this is codomain. Okay, if a function is defined from x to y, a set x to y, this is known as domain and this is known as codomain. This is known as codomain. Okay, the set of all images of that function. Okay, if the set of all images of the function is the range. Range is nothing but the set of all images. It is a set of all images. All right, it is a set of all images of that function. That is known as range. And we know that for a function to be onto every element in y, okay, every element in y should have a pre-image. It is nothing but the codomain itself should be the range, right? So what can you say about the range of the function f? The range of the function should be equal to y. That is, every element in y should have a pre-image, means what will be the set, what will be the set or what will be the range? The range should contain all the elements in y, right? So what is the range of y? Range of f is equal to nothing but y. All right, it is direct application of the definition of onto function. Now we are moving on to the next question, that is the number of 1 functions. All right, the number of 1 functions from a set containing two elements to a set containing 3 elements is what? All right, we have to find out the number of 1 function, that is from a set containing 2 elements to a set containing 3 elements. All right. So how will you find out? It is not given in your textbook. It has a formula. All right. So the formula is if the number of elements, if a function is defined from, okay, if a function is defined from A to B and n of A is equal to, let it be m, and n of B is equal to n. All right, then the total number of one functions, the total number of one function from A to B is nothing but npm, n greater than or equal to m, and 0 if n is less than m. 0 if n less than m. All right, this you have to study. Okay, so using this, we are going to solve this question. That is, here you can say that, here you can see what is n of A. It is given. The first set contains 2 elements and the second set contains 3 elements. So what will be the total number of one function? Just permute the number of elements in the second set with number of elements in the first set. Okay, number of elements in the second set is 3 and we are going to permute it with the number of elements in the first set. That is nothing but 2. What is 3p2? How will you find the value of 3p2? It is 3 factorial by 3 minus 2 factorial. That is nothing but 3 factorial by 1 factorial. So what will be the value? That is nothing but 3 into 2 into 1. That is equal to 6. All right. So how many one functions will be there? It is nothing but 6. All right. So what will happen if n is less than m? N is less than m. I'll show it with an example. If n is less than m, that is, if the first set contains lesser elements than that of the second set, then there will not be any one function, that is 0, right? N less than m is 0, right? There won't be any one function on such a type of set. That is, if you are taking here, n should be less than m, right? So if I'm taking 1, 2, 3, and this one just it would be 5. All right, so this is the number of elements in the second set is n and number of elements in the first set is m. Here you can see that n is equal to 2 and m is equal to 3. That means n is less than m, right? Now you are going to map 1 with 4. All right, then it should be a one function, so I'm going to map 2 with 5. Now do you have any image for 3? Do you have any image for a function? Every element in it should have an image, right? We map 3 to 4. If I map 3 to 4, what will happen? What will happen? It will not be an one function, right? So we know that for a function to be one, it should have a unique image. It is not, 1 is also mapping with 4 and 3 is also mapping with 4. So it is not 1. So we can say that if n is less than m, there are 0 functions. There won't exist any one function. All right. Now what happens if both the set contain same number of elements? That is also a question, right? Then also that formula. If n is greater than or less than or equal to m, we have learned that n is greater than or equal to m. Then what is the formula? It is nothing but npm. All right. So if both are equal, that is if n of a is equal to 3 and if n of b is also equal to 3, then what will happen? The number of on one function will be nothing but 3p3. The number of one function is nothing but 3p3. That is equal to 3 factorial. All right. Okay. 3 factorial by 0 factorial. 0 factorial is 1. That is equal to 3 factorial. All right. So these were some of the questions. That is the multiple choice question which are important in that chapter. And I'll discuss 2 more functions. All right. That is, we have already done a model of that question with a different function. That is, we have done it with f of x is equal to 2x. Similar questions are asked in MCQ. That is, they might ask f of x is equal to x raised to 4. F is defined from R to R. f of x is equal to x raised to 4 f from r to r. They'll give you options like it is either 1 1 or on 2 or both 1 1 and on 2, such type of question. All right, so how will you check whether it is 1 1 and on 2? How will you check? First of all, we can start with 1 1. All right, so here I'm going to take, we know that f of x1 is equal to, for a function to be 1 1, if f of x1 is equal to f of x2, then x1 should be equal to x2. All right, x1 should be equal to x2, then only it will become a 1 1 function, right? So here I'm going to take f of x1. Okay, let x1 be equal to 2. Let x1 be equal to 2. So what is f of x1? F of x1 is f of 2, that is equal to 2 raised to 4, that is equal to 16. Now I'm going to take x2 as minus 2. All right, x2 as minus 2. So what is f of x2? F of x2 is nothing but f of minus 2, that is minus 2 the whole raised to 4, that is equal to 16. All right, here you have got that f of x1 is equal to f of x2. Both are 16. F of x1 is equal to f of x2. But what can you say? Is x1 equal to x2? No, right? x1 is not equal to x2. x1 is 2 and x2 is minus 2. But f of x1 and f of x2 are equal. So more than one element has the same image. 2 has also the image 16. Minus 2 also has the image 16. So it is not 1 1. All right, it is not 1 1. Now, how will you check? It is not on 2. Let f of x is equal to 2. All right, let f of x equal to 2. Can you find an x value for which f of x becomes 2? That is there any x that satisfies the condition x raised to 4 equal to 2? Any number raised to 4 cannot be equal to 2, right? So no number, no value of x satisfies that particular thing. That is, f of x cannot be equal to 2. And we know that 2 belongs to R. Right, f is defined from R to R, which means R has the element 2, but 2 has no pre-image, which means it is not on 2. It is not on 2. All right. Now, there is another function also, similar type of question they may ask. F of x is equal to the greatest integer function. Okay, greatest integer function x. That is also defined from R to R. Okay, it is also defined from R to R. It is nothing but the greatest integer function. What is greatest integer function? If you are given 1.2, they will round it to the nearest integer, right? Nearest greatest integer. That is nothing but 1. So this is what do you mean by greatest integer function? That is greatest integer of 1.2 is 1. That is, they are rounding off to the nearest integer, which means 1.3 is also 1, right? Which means 1.5 is also 1. The value of greatest integer 1.5 is also 1. So here you are getting, for different values of x, you are getting the same f of x. Okay, here you can see that if this is x1, this is x2, and this is x3. For different x1s, we are x values, we are getting different images. All right. I'm sorry. So we are getting different values of f of x for so same values of f of x for different x1s. So clearly it is not 1 1. All right. Now, what about if I take the value f of x is equal to 1.2? All right. F of x is equal to 1.2. It belongs to R. All right. So is there any x that satisfies the condition, that is greatest integer will be equal to 1? Is there any x that satisfies this condition? No x will satisfy this particular condition, right? So we can say that for every element in R, it doesn't have a pre-image. So we can say that the greatest integer function is not onto also. So It is not one as well as it is not onto. All right. So these were the important questions in that chapter, relation and function. I hope it was useful to you. All right. So thank you.